We are going to start off by just listing the 4 power series that we spent time on last time and write a generic power series. So, series that you should know, the very first one was the exponential function. We saw that e to the x is equal to, and I'll write down a few terms and then I'll write down the summation shorthand notation. And part of what we need to do in these power series problems is we need to be really good at finding patterns. That's good. So, the exponential function is an important one, and we talked a little bit about composition of functions, and so there might be some times where it would be appropriate to identify a power series solution that you're coming up with and then say, hey, that kind of looks like the exponential function. Now, a lot of them are going to look like the exponential function, but it's really not going to be. So you really have to be good at identifying the components of what makes something a series an exponential function versus something else. We saw the sine and cosine, and the thing that I asked you to try to remember was that sine is an odd function, cosine is an even function, and if you know that, then those are the pieces of the exponential function that goes with the sine and the cosine with alternating signs. S-I-G-N sign, as opposed to S-I-N-E sign. And if you could tutor Calc 2, they're doing series right about now, so that would be really good for you. Yes, if you understood series in Calc 2, then it's just a matter of reviewing. If you didn't understand series, well, maybe you should. Oh yeah. Want to understand series. All right, so the cosine is even, so we have even powers including the constant. And then the last one is a series that probably won't be coming up too much, but I think it's an important series to know in general because it's simple enough to be able to identify So these are the 4 important series, and you can, especially this last one, you can integrate and take the derivative of that particular function to come up with a couple more new series. If you take the square, if you replace x with x squared and then take the antiderivative, that's the arctangent. So it really, this one series down here really can spread out to a lot of different types of functions. If you take the integral of this, it's a logarithm. So now you can develop series for logarithms and develop series for arctangents and things like that. What we didn't talk too much about was the idea of combining series, but we'll just jump into that as we start doing examples.
What do you do when you have, instead of a 1, you have like a 9 or something?
If you have a 9, then you probably want to factor it out and call it 9 over x down here, and then you'll have a constant out on the outside. We'll talk about that if we run into it. So in general, and I think this is where we left off last time, any function that you have can be seen as a series, or if you have a series, it could be seen as a function, even if you can't find a nice pattern. There eventually will be some sort of pattern. But a series can be written as some constant times x minus some value to the kth power. And all these series that we were talking about are all centered around 0. So x naught is equal to 0. And I think we called it a Maclaurin series. And for the most part, we're going to stick with Maclaurin series because those are the easier ones. But there might be some cases where you're doing a homework assignment, or maybe some case where you're doing something in your future classes in engineering or whatever, where you're trying to solve a differential equation where you're not centered around 0. Then you just have to apply your shift. So this is our general formula for a series. Okay? And when we start looking at differential equations, we'll start by looking at problems whose solutions we already know so that we can verify our series solutions. But this could be applied to any other differential equation whose solutions we don't know. But what we're going to do is we're going to assume that your function looks like this, and then we'll go from there. All right? All right, so let's get started with an actual differential equation, and let's get started with a simple differential equation that we know. And this should be one of those things where if I see you walking down the street this weekend and I say, what's the solution to this differential equation, you should be able to tell me. Okay. So this is a first order differential equation. It's homogeneous. It has constant coefficients. It's linear. All right. Yeah, it's also separable, so you could have approached it that way. Yeah. So let's start by looking at this. No, we don't know what it is. Let's pretend we don't know what it is. Okay. So some of you have the solution to this already in your head. Some of you don't. So let's see if we can find the solution using series. So we're going to assume that your function, your solution, is a power series that looks like this. And according to this differential equation, we need to figure out when what y prime is. And so we had practice in taking derivatives of series. And we know that when we take a derivative of a series, because a series is just a sum of a bunch of terms, a differentiation is term by term differentiation. So we just take the derivative of each term, and then we can kind of wrap it back up together into this symbol. So using the summation, if we take the derivative of this, we have ck is constant, and we have another k, x to the k minus 1. And I think I also mentioned this idea that when k is equal to 0, this is not going to make a difference whether we leave 0 here or not, but just for efficiency, we kind of said that we're going to do a shift in our series. Yeah.
That's for whenever you take a derivative.
That's when you take derivatives, you're going to do that shift. So if we just literally just plug it into this equation, we will get the sum of k goes from 1 to infinity of ck k x to the k minus 1 plus y, which is just the original series, k goes from 0 to infinity of ck x to the k, and then this is going to equal to 0. Now you have two things to do. One is to combine the summations into one summation on the left-hand side, and the other thing to do is to, what's the other thing? Is to find a pattern for your unknown constants, ck. So we're going to set that up one by one. Now as you combine things, because your series shifted, right, there's going to be several ways to try to combine this into one. One way is to take this k is equal to 0 as something totally separate and then just take that out and then see if you can deal with that later, and then you have a summation from 1 to infinity of just the terms. The other way is to write out a few terms of each of the series and see if there's a way to combine it that way. So I think writing out the first few terms is a little bit more revealing, and then maybe once you get used to that, you can do it with less and less writing out. So let's write out a few terms for the first series. K starts with 1, so I have C1, K is equal to 1, x to the 1 minus 1, that's just 0, right? And then when k is equal to 2, I'll have C2, k is equal to 2, x to the 2 minus 1, which is x. And then k is equal to 3, I'll have 3c3 x to the second power, x to the 3 minus 1. So we can get a feel for how that's going to work out. Now let's take a look at our second series, where it's just ck x to the k, where k goes from 0 to infinity. So we'll start off with c0, x to the 0, plus c1 x plus c2 x squared, and then we'll just say dot, dot, dot. Okay? this whole thing is supposed to be equal to 0. And what we're going to do is collect the terms that have common terms with the degrees of the polynomials, or with the power functions. So I have C1 plus C naught. That's a constant. And then the linear terms will be 2C2 plus C1 times x to the first plus yeah, because they came from that same series. They came from the same power function.
Okay.
So the next one is 3C3 plus C2 times x squared. Okay? Now, in this particular scenario, we have this thing is equal to 0. It's a homogeneous differential equation, so everything's going to be set equal to 0. So this is your combining business. And then so from here, you're going to take each of these coefficients of the combined power series, and then you're going to set that equal to whatever the right-hand side is. In this case, it's a homogeneous, so it's equal to 0. If we had a function here, we would have needed to have found the series for that and then come up with a bunch of these equations that you have to solve. So this is equal to 0, and then we have
Undetermined coefficient, basically.
yeah, so we have a bunch of unknowns. Now, this is an infinite series, so if we were to write this out and thinking linear algebra, well, this is n equations and n unknowns business. This is an infinite number of equations and an infinite number of unknowns. So that's not going to be helpful. The linear algebra techniques won't be helpful for us in solving for this. And so the key is that you have to be good at looking for patterns. So this is what we have so far. And so one of the keys for trying to find patterns is to look at the first set of equations that you need to solve, and then imagine what the rest is going to look like. Okay? So I'll let you think about that for a few minutes. Meanwhile, we're going to see if we can start solving for this. So we have a relationship between C1 and C naught. So from here, I'm going to say that C1 is equal to negative C naught. Does that look okay? And then C2 is going to equal to, it's going to be negative C1 divided by 2. Is that correct? But what is C1 equal to? So we have to kind of domino back to the original. C1 is equal to negative C naught. So this looks like it's going to be a plus. It would be C naught over 2. So something interesting here is happening. It looks like, well, let's do it one more time. Here C3 is equal to negative C2 divided by 3. Oh, but what's C2 equal to? C2 is equal to negative C1 over 2. Oh, let's just say it's C naught over 2. So this is negative C naught over 3 times 2 over 6. Should we put 6? Now let's put 3 times 2. Okay? So this is another thing that you're going to have to try to do and get used to, and that is to know when to multiply and know when to not multiply. And a lot of times when you're trying to find patterns, it's best to not multiply just yet. There might be some products where it might be obvious to say, hey, let's multiply this out, and others that might not. So, did you guys figure out what the dot dot dots might be? Let's see if we can anticipate something. If we can't, we can actually go back here and extend a couple of more terms for our powers. But let's see if we can go back over here and imagine what the next term is going to be. What should it be? 4C4 plus C3 is equal to 0. Okay, so we would have gotten that if we would have extended this out. And then if we did have this, we can say that C4 is equal to negative C3 over 4. And that dominoes back again to C naught. So this is positive C naught over 4 times 3 times 2 times 1. Yeah, so it's the factorial. All right. So now I'll put the dot 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 here, and let's see if we can rewrite this now as a power series that we're supposed to be dealing with.
So we have to do this in this kind of power series.
Yeah. Well, we're going to put it back because our original claim is that y is equal to this power series, whatever it might be. And if we can identify that power series that we're going to come up with, then that's great. If not, then then those are going to be your answers, and then that's the best you can do. But in this problem, you know what the answer is, right? Okay. All right. Some of okay. All right. So negative C naught. Oops. Sorry. Your power series starts with 0. So your power series actually starts with C naught. Right? And from here, we have, I suppose I should have written it here. It'll be C naught plus C1x plus C2x squared plus C3x cubed plus C4x to the fourth. So I have C naught plus C1, looks like it's negative C naught times x. So C1 is negative C naught, and then I have times x over here. Plus C2 is C naught over 2, and then that is being multiplied by x squared. C3 is negative C naught over here. I'm just going to write 3 factorial, x to the third. And since we did C4, let's do that too. So this is going to be a positive C naught over 4 factorial x to the fourth plus dot dot dot. Anything we can do? Let's factor out the C naught, right? So we have a 1 minus x plus x squared over 2. Let's throw in a factorial there. Minus x cubed over 3 factorial plus x to the fourth over 4 factorial. So it's alternating, so it kind of reminds me of sine and cosine. But it's not all even or it's not all odd. So now it kind of reminds me back of the exponential function. So what do you think this is equal to? Let's see if we can. It kind of looks a lot like the exponential function, right? Except the sign changes. So what if it was e to the minus x? Let's see. 1 plus negative x plus negative x squared over 2 factorial minus negative x to the third over 3 factorial. Yeah. Negative x to the fourth over 4 factorial. So this looks a lot like the exponential function, except instead of having x in there, you have negative x. So this looks like it's C9. Look, we even have the arbitrary constant for us, right? And then we have e to the negative x. How's that? Well, the thing is that if there's a differential equation that we can't solve using any of the methods that we have, then the best we could do is approximate with a series. And so that's like that integral of e to the x squared business. We can't integrate that because we don't have a function for that. And so we can use series to do an approximation of that. I suppose. Because we have to learn it.
Well, I know that. But I want to see like the ones that we actually use.
Well, I think we need to ease into this. Yeah.
Didn't we do something to that e to the x squared? Didn't we like change the variables around? Or was that the double integral?
That was probably a double integral. We made it to a double integral, and we actually found the area under the curve, under the bell curve. All right. So this is your solution, and this should have been what you were thinking of when you saw this differential equation, right? Right. Of course. So I think it's good to do this for differential equations that we have the answers for, so we can verify that this actually works. And then our deal is to find patterns. Okay, so I think we're going to do one more. And we're going to extend ourselves to a second order differential equation. Maybe we should even throw a right-hand side to it. Ooh. See if I have any examples in my notes. Oh, let's see if we could do an example from homework. We're on 6, right? They're all homogeneous. All right. Well, let's do problem number 2, for example. Okay, so here's our differential equation, and we have a second order differential equation. So let's see if we could deal with this. We have y is equal to the sum going from 0 to infinity of ck x to the k. It looks like we need the first derivative and the second derivatives, right? So the first derivative is the sum of k ck x to the k minus 1. K goes from, remember the shift, 1 to infinity. And then our second derivative is going to be the sum of k minus 1 ck x to the k minus 2. K goes from 2 to infinity, right? So let's put in those values for y double prime. We got the sum, k goes from 2 to infinity, k minus 1 ck x to the k minus 2, plus, now there's an extra x squared here that's going to get distributed here to an infinite number of terms. We can choose to do that now or later. Let's do that a little bit later, because you're going to have to write this in over 2 or 3 pages anyways. K goes from 1 to infinity of k ck x to the k minus 1, plus another x that's going to be distributed to the y function, ck x to the k. K goes from 1 to infinity. 0. Well, it would, but now we're going to distribute this so that, you know, the powers aren't going to be all the same, and so this is especially now would be a good time to write out the first couple of terms and see if you can find some sort of pattern. Luckily, this is equal to 0, so all the coefficients going to be 0. So if you can find a way to shift this so that it's all the same, should we do that? Maybe we should do that. Maybe we should do an exercise in shifting the indices. So let's multiply out the x squareds. So k goes from 2 to infinity, k minus 1, ck x to the k minus 2, plus the sum k ck x to the, now if I'm going to add or if I'm going to multiply each term by x squared, my power for x is going to go up by 2. So what's my power for x here? K plus 1 plus the sum k goes from 0 to infinity of ck. This is also going to be k plus 1. Now I'm kind of interested, maybe we should do this in the other problem where it was a little bit easier. I'm kind of interested in adjusting my index and my x power so that it's all matching, it's all the same. So let's see. imagine these k's over here, and I want it to be the same as the power for x. So I want this k to have the same power as these x's over here. I want this x to the k minus 1 to be the same power as x to the k minus 2. K plus 1. K minus 2 to be the same power as k plus 1. How many x's, or how much do I need to adjust k by to get that? I need to add 3 to the k here, right? So I would have, I'm interested in having x to the k plus 1, so it'll match with all these things. So if I add 3, if I make this k, add 3 to the k, or if I replace k with k plus 3, I'm going to get k plus 1, right? So k needs to get replaced with k plus 3. That means all the k's in my expression here needs to also shift, right? So this is c, k plus 3. This is k plus 3 minus 1. What's that? K plus 2. And k gets replaced with k plus 3. Is that okay? No? Yeah, you want the powers to match, because the main idea here is to come up with combining like terms, and your like terms are with x's and stuff. So you want the powers to match. So is the inside of this series okay? If it's not, is there a way you can ask the question, like, how did it, what happened? I basically replaced all the k's with k plus 3 because that was the amount of shifts that I needed to get this to match up. Did that work? All right. What? So I replaced everything in this series. I replaced all the k's with k plus 3. So that I would have matching. Now, in shifting the inside of your series, now you have to shift your index as well. Does that make sense?
Don't you have to shift the index back home?
So the shift in the index is actually going to be the opposite from the shift in. So you do subtract. So k now has to start from, oh, we have to subtract 3. K has to start from -1. What?
No.
Okay, here's the thing. Well, I think more importantly, we need to get the powers of x to match. So the thing is that these two series are exactly the same. And you can do that, you can check by writing out the first few terms of each of these series. So when k is equal to 2, you put 2 in for k. You put 2 in for k, 2 minus 1 is 1. You got c sub 2 x to the 0 power plus when k is equal to, the next after 2 is 3. When k is equal to 3, this is 3 times 2 c3 x to the first power. Okay, so that's how the first series looks like. And now if we did this adjustment correctly where we shift the index and shift the k's, we should get the same thing. So what happens if we put a negative 1 in for k? Negative 1 in for k, we have negative 1 plus 3, which is 2. Negative 1 plus 2, which is 1. Negative 1 plus 3 for the subscript is 2. And then negative 1 plus positive 1 is 0, so that's the power. And so we're matching. Okay, if you didn't shift the index, you wouldn't get the exact same series. You get the series starting at a different place. So we'll see that we would get the same series by doing the shift. So the key is that whatever you do to the k's inside of the series, you do the opposite to the starting point. So we took all the k's and we replaced it with k plus 3. Now we're going to take the starting point, which is 2, and then instead of adding 3 to it, we're going to subtract 3. Okay? So that's how you shift indices. It's really simple if you just remember that little trick. Okay. So now that we have this, we have the same powers for x, which is good, except this one has, I start two of them. Is this a 0 or a 1? Can't read my own writing. I hope you can read my writing. No, that's besides the point. You guys are just... So I have k started from negative 1, I have k starting at 0, and k starting at positive 1. So it looks like there's going to be a few extraneous terms. So what I want to do is I want to select the largest starting point, k, and then all the other ones that start before that, I just want to write out those first few terms. Okay? So for this one, I'm going to write out when k is equal to 1 or negative 1 and when k is equal to 0. And then for k starting at 1 after that, I'll just write the series. So let's see if you understood what I meant. Oh, negative 1. So when k is equal to negative 1, I did that already in the other page, right? I have 2c2, that's it. So 2 times c2, right? So that's this series over here when k is equal to negative 1. When k is equal to 0, I have 3 times 2. C3 and x to the first power. Plus, now that I have those first two terms out of the way, I can just rewrite the sum. K goes from 1 to infinity of k plus 3, k plus 2, ck plus 3, x to the k plus 1. So that's the rest of the series. So I took this series here in green. I just took the first two terms of the series, and then the rest I wrote like this. All right? So that's one. That's the first one over here, the y double prime. Now let's take this one. Well, this one is already starting at k is equal to 1, so that is already going to have a matching index, and we know that the power is matching, so let's just rewrite that whole thing over again. K goes from 1 to infinity, k, ck, x to the k minus k plus 1. Okay. Now the third one, I'm going to take care of the k is equal to 0 term, and then write the rest starting from k is equal to 1. So the rest of the series here will start when k is equal to 1 to infinity ck x to the k plus 1. When k is equal to 0, I have c0 times x to the, times x to the first power. This one? Up here?
First term.
First one?
No.
The first one?
No.
K.
What happened after? I just got stuck after the arrow.
After the arrows, I rewrote this whole thing. Nothing changed.
Okay.
Now for this one,
Oh, you changed your mind. You wanted to
because it started at 1. The indices, we want the indices to be all starting in the same place.
Okay.
So what do we have? We have some loose terms outside. We have loose terms that are outside of the summation, any of the summation. So we have 2c2 plus 2 times 3 c3 times x plus c sub 0 times x. So these are all the loose terms that are on the outside. Plus I have a sum of all these terms now that are all like terms, which means I can combine them with the same x to the whatever power, right? So let's see if we can combine them. I have k plus 3 times k plus 2 c k plus 3 plus k ck plus another ck. I suppose we could have combined those two. But they're all coefficients of x to the k plus 1. So we have 2c2 plus 2 times 3 c3 plus c0 times x plus this sum, k goes from 1 to infinity, k plus 3, k plus 2, c k plus 3 plus, and I'm just going to combine these two, k plus 1, ck. All right. All right, we're halfway there. Is that good? Oops, where'd it go? Let's see. All right. Now, this is all supposed to be equal to 0. So let's get started with trying to figure out what this might look like. We have the first one as a constant term. So let's just call that 2c2 equals 0. So c2 looks like it's going to be equal to 0. I'll write that out a little bit later. We got 2 times 3c3 plus c0 is equal to 0. So I'm always interested in the higher term in terms of the lower term. So we'll bring the c naught on the other side and divide by, looks like it might be 3 factorial. But we'll do that a little bit later. But now I'm more interested in trying to set up the other equations that we're going to come up with. So remember, infinite number of equations, infinite unknowns, so we'll just do the first 4 or 5. So when k is equal to 1, now we take this term over here and put 1 in and set it out equal to 0 because the coefficients are all 0. So when k is equal to 1, I have x squared, so it's like my x squared term. When k is equal to 1, I have 3 plus 1 is 4. And it's 4 times 3, c4. Plus, when k is equal to 1, I have 2 c0 or c1, right, when k is equal to 1. So now we have some information about that. This is the summation now when k is equal to 1. I need to know k is equal to 2. Maybe we'll go one more, k is equal to 3. Yes. It's homogeneous. It's going to be equal to 0. No, it's the same thing. It's still equal to 0. When this is non-homogeneous, you would need to find a series for it. And then it gets a little bit more complicated. Just a little. So k is equal to 2. Let's put 2 in for k. This looks like it's 5 times 4. K is equal to 2. This is going to be c5. And then k is equal to 2. This is going to be 3, c2. And then when k is equal to 3, this is going to be 6 times 5, c6, plus k is equal to 3. This is going to be 4, c3. Yeah, that's up here. We didn't skip it. We still we wrote it out separately outside of that, and it's still here as part of our equations. So we didn't skip it because it's needed here. Okay? Yeah. Yeah. So let's see if we can find a pattern. Again, some of them you'd be able to find a pattern, some of them you won't. So let's see if this one has a pattern. If you can't find a pattern, then you're not going to be able to write your solution as a nice function like nice functions that we have. You just have to keep it as a series. So that's going to, C5 is also going to be equal to 0. Okay? So C3 is equal to negative C naught over 3 times 2. C4 is going to be negative 2C1 divided by 4 times 3. And we don't have any other information about C1, so I think I would just leave it like that. And I'm not going to cancel too many things yet until I see more of a pattern. C5 is equal to 0, because C5 is going to be something with a C2 in it, and C2 we know is equal to 0. Looks like we might need to find a couple more terms, but let's write out this last one. C6 is going to equal to negative 4C3 divided by 6 times 5. Now we do have something for C3, right? C3 is equal to, so this is negative 4, and then C3 is equal to negative C naught 2 times 3 divided by 6 times 5. So let's see, this becomes a positive 4C naught divided by 6 times 5 times 3 times 2. Well, that doesn't look nice. So we'll just write it like that. I suppose we can cancel some stuff out, but there's not looking like there's any nice things to cancel. All right. So I think I might be interested in doing one more. It's all about finding patterns, so go as far as you need to until you see a pattern. So when k is equal to 4 in this series, we have 4, this is 7 times 6, C7, plus k is equal to 4, this is 5C to the C sub 5, C sub 4. So this tells us that C7 is going to be negative 5 C4 divided by 7 times 6, which tells us that this is negative 5. C4 was negative 2 C1 4 3 divided by 7 times 6. So negative negative is a positive. We have 5 times 2 C1 over 7 times 6 times 4 times 3. I can't find a pattern here. Okay. Yeah, we can divide. If we're set on saying that I can't see a nice pattern here, then you can just go ahead and simplify it, which is where I'm moving towards here at this point. All right, so let's see what our situation is. Our situation is that what we're finding here are the coefficients for a power series that is supposed to be the solution to this differential equation. So in the end here, what I'm interested in writing is the power series y is equal to C0 plus C1 plus C1x plus C2x squared plus C3x cubed plus C4 x to the fourth, etc. And so what I'm finding here is that we have a C naught and C1 are your arbitrary constants from your general solution. Remember, this started off as a second order differential equation. So it looks like they would be your arbitrary constants, and it looks like your power series here is going to split up into two functions, one with an arbitrary constant C0 and the other one with an arbitrary constant C1. So I'll have C0 plus C1x. Okay. Now C2 is gone. So let me just put 0 here. And then I'm going to have one more line where I'm going to split up the two different functions. And now I have a C3, which is negative C0 over, let's just say over 6, since we didn't really find a good pattern. C4 is negative, again, canceling some stuff out, C1 over 6. Over 12, but then there's a 2 up here, right? So is that right? Just want to make sure that we're good here. Our C, x to the third, x to the fourth. We don't want to leave our x's out. Our C5 is 0. Our C6 is 4. Oh, let's cancel the 4 and the 2 and the 4 and the 6. So that leaves 45. So C0 over 45 x to the 6th. And then this one, the 5 doesn't cancel, so we're stuck with a 5. And then oh, now that's too big. So you guys figure it out. 5 C1 over, it looks like I need, I took one of the 2's out, so I have 252. The 5 doesn't cancel, so I'm going to leave the 5 there. Okay, so this is our series, and this is since this is a second order differential equation, the last thing left to do is to combine all the C0s together and factor out that C0. So C0, and then we have a 1 minus x cubed over 6 plus x to the 6th over 45. Not seeing a pattern, so you're just going to have to write it like this. So I see that it looks like it's going to be a plus minus, so I see that pattern. And I see that I have x cubed, x to the 6th, so the next one's probably going to be x to the 9th. But again, the coefficients there are kind of tripping me out, so I'll just leave it like that. Plus, we have a C1. Everything that's a C1 can get grouped together. So C1, and then we have an x minus x to the 4th over 6 plus 5 over 252 x to the 7th plus dot, dot, dot. Okay? So these are your two functions that we were not able to identify as something that we know, but we have a power series solution that looks like this. So y is equal to this whole thing. All right, let's see if we got it right. So, oh, it's the one with the correct answer. I'll figure it out. But it is right, right? You got 1, 1, 6, 1, 45, and then 6, 5, 252. We even got those coefficients right. All right, so it looks good. So here is a function which we cannot identify, but at least now we have a power series solution for it. There are 5 questions. Each of them will take about a page and a half, and it'll take you about half an hour to an hour to do. Good luck.